So, now we'll see the difference between neo and tertiary. Don't get confused between neo and tertiary here. Look at this compound. Total number of carbon atoms 1, 2, 3, 4, 5. 5 carbon atoms are there. So it is pentyl group. And if you want to write it as prefix as iso, except one carbon atom, other carbon atom must be in the straight chain. That is clear for you. How many carbon atoms are there? 5. 5 minus 1 is 4. Now how many carbon atoms are there in straight chain? Only 3. So that we cannot write it as a prefix as iso to this compound. And to write iso, there must be one propyl group must be there, but here there is no propyl group. Now iso we cannot. Now one more is it is not secondary primary. This compound, this carbon I am telling, this is second primary. It's sorry, this carbon atom is directly attached to the primary one carbon atom, hence it is primary. Now this carbon atom is directly attached to the 4 carbon atoms, hence it is quaternary carbon, and this carbon containing 3 CH3 group, that is methyl group, hence prefix is neo. Now number of carbon atoms 5, hence neo pentyl chloride. Neo pentyl chloride, this compound, that is common name. IUPAC name is 1, 2, 3, 1 chloro, 2,2 dimethyl propane, right? 1, 2, 3 or 1, 2, 3, 1 and the same. At first position one chlorine atom is there, hence 1 chloro. At second position 2 methyl groups are there, 2,2 dimethyl propane. IUPAC name is clear for you, hope so. Now this compound, how many carbon atoms are there? 1, 2, 3, 4. 4 minus 1, 3. If you want to write prefix as iso, there must be 3 carbon atoms must be there in the straight chain, but here there are only 2 carbon atoms are there in the straight chain. And if you want to say like this, 3 carbon atoms, but we cannot say it as iso. Why? Because there must be CH3, CH2 group must be there. That is propyl, isopropyl group must be there. One carbon atom must be there as branched, and other remaining 3 carbon atoms must be present in the straight chain. Now this carbon atom is directly attached to the 3 methyl group, 1, 2, 3 methyl group, but there is no one more carbon atom there is no one more carbon atom. It is directly attached to the chlorine atom. Hence, if there is one more carbon atom and chlorine, then neo. Right? This carbon must be attached to 4 carbon atoms. Out of 4 carbon atoms, 3 must be methyl groups. But here, this carbon atom is attached only 3 methyl groups. Hence, this is a halogen atom directly attached to the carbon atom is containing 3 carbon atoms. Hence, this compound is tertiary 1, 2, 3, 4 butyl chloride. Tertiary butyl chloride. Hope it is clear for you now. Next, I will discuss about homework problems. Very few of you submitted homework. You should not repeat this. And today I will discuss the homework problem. But next onwards I am not going to discuss. Everyone should submit the homeworks and I will take the attendance. So here CH3, CH2, CH3, CH3. How many carbon atoms are there? 1, 2, 3, 4, 5. 5 carbon atoms are there. And this is as a parent, it is a pentane. Parent compound is pentane. At what position bromine is attached 1, 2, 3, 1, 2, 3, third position. From this side or from this side it is one and the same. Hence, IUPAC name of this compound is 3-bromopentane. Right? 3-bromopentane. Now, common name. Here, you can see straight chain, and to this carbon atom, one bromine is attached, one hydrogen is attached, and 2 carbon atoms are attached. I will write it as like this. Okay. Now, to this carbon, one hydrogen, 2 carbon atoms are attached, hence this compound is a secondary. Why we cannot use iso as prefix? Now it is clear for you. Why? To write iso as prefix, this bromine atom should be primary, should be there at the one end, and at the second carbon atom there must be a branch, right? There must be one straight chain and one carbon atom in the branched chain. Hence, name of this compound is a secondary. 5 carbon atoms are there. Hence, pentyl bromide. Hope it is clear for you. Now, look at this compound. Total 1, 2, 3, 4, 5, 6 carbon atoms are there. And this carbon atom is attached to the 4 carbon atoms. Out of 4 carbon atoms, 3 are methyl groups, and this is primary compound. Here, bromine attached to the carbon atom is directly attached to the one more carbon atom, hence it is a primary. Here, this is primary carbon atom. Now, name of this compound is, common name I will write first, neo. Why neo? This carbon atom is directly attached to 4 carbon atom. Out of 4 carbon atoms, 3 are methyl groups. Neo, how many carbon atoms are there now? 1, 2, 3, 4, 5, 6. Hexyl, neo, hexyl, and bromide. Neo, hexyl, bromide. Now, IUPAC name, consider longest chain. Which one is longest chain? 1, 2, 3, 4. 1, 2, 3, 4. So, one and the same. Or 1, 2, 3, 4 or 1, 2, 3, 4. And substituent or functional group should get a least number. So, that I will number from here 1, 2, 3, 4. Now, name of this compound is alphabetical order. First bromo comes. 1 bromo. At the third position, 2 methyl groups are there. That is 3, 3. How many methyl groups are there? 2. Dimethyl. Straight chain is butane, right? Dimethyl butane. Hope it is clear for you. Now, third problem is a benzyl halide. Let us see common name. Okay. And then IUPAC name. So, we have to consider if it is primary compound, now it is secondary compound. Why it is secondary compound? This carbon is directly attached to the 2 more carbon atoms. Hence, it is a secondary benzylic halide. So, in benzylic halide, in common names, we are named as benzyl halide or alkyl halides. So, name of this compound is, see here, I will consider this carbon as a alpha carbon and this as a beta carbon. So, this containing functional group here, it is directly attached. This carbon is directly attached to the functional group, and I will consider this as alpha and this as a beta. Now, in common system of nomenclature, we can write it as alpha, here it is phenyl, right? Alpha, at alpha position, phenyl group is there, and two carbon atom containing two carbon atoms, hence it is ethyl chloride. Okay, alpha, in alpha position phenyl group is there, hence alpha phenyl, it is ethyl chloride. Ethyl chloride we should name as alkyl halide, ethyl chloride. Hope it is clear. Now if it is primary, just benzyl chloride is enough. Instead of here CH3, one CH2 group is there, means that is directly we can name it as a benzyl chloride, but here one CH3 group is attached, hence we name it as alpha phenyl ethyl chloride. And the IUPAC name of this compound, for this compound is, see, in primary compound, we saw primary compound there was only one carbon atom. In last class we discussed only one carbon atom. Here there are two carbon atoms are present, so that parent is ethane, right? Ethane. So in IUPAC system of nomenclature we are using numbers 1, 2, 3, etc. Alpha beta only in the common system of nomenclature. I will take this as this position as 1, right? It should functional group should get least number, and this as 2. Now name of this compound is, at first position what is there, 1 chloro 1 phenyl, right? At first, for first position one chloro group is attached, 1 chloro, this is based on alphabetical order we have to write, 1 chloro 1 phenyl, 1 chloro 1 phenyl, and parent compound is ethane. The parent chain is ethane, hence it is 1 chloro 1 phenyl ethane. Hope it is clear for you. So 3 homeworks. First one is 3 bromopentane. Clear it is 3 bromopentane, and secondary pentyl bromide is clear. And here it is neo, it is common name, and IUPAC name however you are knowing, and common name here we are using prefix, one prefix as alpha, it represents its position. Next we'll discuss about physical properties. In last class we stopped there in physical properties. I'll continue from there. Physical properties of haloalkanes and haloarenes. First I'll start with the state. Okay, state. We discussed about this, about melting point, boiling point and density we discussed. Otherwise I'll start with the state. So some lower alkyl halides like methyl chloride or methyl bromide or ethyl chloride are gaseous. Okay, these are gaseous. Some higher alkanes are liquid or solid, present as liquid state or present in a liquid state or a solid state. It's about a state. Now about haloarenes. Most of the, almost all haloarenes are liquid or solids. Okay, all are liquids or solids. In haloalkanes, some lower haloalkanes are gaseous in nature, and some higher alkanes, higher not alkanes, halo, we are discussing about haloalkanes. Haloalkanes are liquid or solid, and haloarenes are liquid or solid compounds. Next, second one, first one is state, second one is order. Okay, in order, some volatile compound gives sweet smell or sweet odor. Okay, volatile compounds are sweet, shows or gives sweet odor. Third one is color. In pure state, these are haloalkanes or haloarenes are colorless. Okay, in pure state, these are colorless. But on exposure to sunlight, chloriodides and bromides impart color. Okay, on exposure to sunlight, if these compounds exposed to sunlight, iodides and alkyl iodides or alkyl bromides impart color. Okay, otherwise in pure state, alkyl halides are colorless and bromides and iodides gives color on exposure to sunlight. This is about state, order and color. Next, I'll discuss about melting point and boiling point. I have already discussed, but it's very, very important concept. Once again, recall that concept, okay? Melting point and boiling point. That is a fourth physical property. Melting point or boiling point. Let us discuss about boiling point of haloalkanes. This boiling point of haloalkanes are directly dependent on, already discussed, on first one, dipole-dipole interaction. Okay, or van der Waals force of attraction. You know, under van der Waals force of attraction, dipole-dipole interaction will come. After that dipole interaction, then dipole and induced dipole interaction, or induced dipole interaction. You already studied, right? Dipole interaction in if there is partial positive and negative charge, then we can observe dipole interaction. If one compound is charged, another is neutral, then we will observe dipole and induced dipole interaction. If both the compounds are neutral or non-polar compounds, in case of non-polar compounds, we can observe induced dipole interaction, or dispersive interaction, dispersive force we can observe, or also called London force of attraction interaction, right? You already studied in your first PUC, right? Is so that boiling point is directly dependent on a dipole-dipole interaction or a van der Waals force of attraction. Okay, dipole-dipole interaction or van der Waals force of attraction. Here it comes under van der Waals force of attraction or intermolecular force of attraction. There dipole-dipole interaction also comes, and one more thing is London force of attraction comes. London force of attraction is between non-polar molecules, right? If you take two hydrocarbons containing only hydrogen and carbon, there you can observe London force of attraction, non-polar, right? So this London force of attraction or van der Waals force of attraction is directly dependent on molecular weight, right? So that boiling point of compound increases with increase in molecular weight of the compound, right? Boiling point increases with increase in molecular weight of the compound, right? Or boiling point decreases with decrease in the increase in branching. In isomers, if you take one straight chain and one branched chain, two isomers, if it is branched one, we can observe lower boiling point compared to straight chain. We'll discuss about that. Hence, I'll explain this by taking few examples. First one, boiling point increases with increase in molecular weight. Let us see about that. I will take example. Any example? Alkyl chloride, alkyl, start with fluoride, fluoride, alkyl, chloride, alkyl bromide and alkyl iodide. Okay. According to this, boiling point increases with increase in molecular weight. Which one will shows greater molecular weight out of these compound? This alkyl iodide shows a greater molecular weight because of the presence of this iodine, or it has a iodide. How it boils? First of all, first I'll take RX. Okay, alkyl halide. These alkyl halides are highly polar in nature. Why polar in nature? Because of the high electronegativity of a halogen atom. These are polar in nature, hence charge separation takes place, delta positive and delta negative. There will be few other molecules. In a compound there will be many molecules will be there, hence RX. I will take one more alkyl halide. Like that, many molecules will be there. Here also it R groups takes a partial positive charge and halogen acquires partial negative charge. What happens? These partial negative charge and partial positive charge will attract. Right? This partial positive and negative charge will attracts, and hence we'll get one molecule. Molecule means many molecules combined together. SARX, many molecule will be there in the compound. Here these partial negative and partial positive charge attracts will be in the dipole-dipole interaction. To boil this compound, we should break this bond. Okay, there must not be any dipole-dipole interaction. So you should supply enough energy to break this dipole-dipole interaction. Then your compound will boil. Hope it is clear for you. Because of the presence of dipole-dipole interaction, we should break that dipole-dipole interaction. Then your compound will boil. So here, as molecular weight increases, what happens? As molecular weight increases, here Ri, here molecular weight of iodide is more. Hence, number of electrons also more. As we move down the group, fluorine, chlorine, bromine, iodine, right? Number of electrons will be more there in iodine, right? Hence, there will be more interaction, right? If this alkyl iodide, in alkyl iodide, and one more, if I take alkyl iodide, partial positive charge, here partial negative charge. Here there will be a more interaction between this iodide and alkyl group. Why? Because here there will be more number of electrons compared to other halogen atoms, and it is not tightly bounded to the nucleus also because of the larger size. Hence this bond will be stronger, right? Intermolecular force of attraction will be greater, but this bond, this alkyl and iodide bond is weaker, but this bond will be very strong. We should break, to boil we should break this bond. Hence, greater the molecular weight, greater will be the boiling point. It depends on dipole-dipole interaction or van der Waals force of attraction. And one more thing is boiling point decreases with increasing branching. I'll take one example. CH3, CH2, 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 Cl. Okay, butyl chloride. One more example. I'll write this isomer CH2, CH2, Cl, 1, 2, CH3, CH2, CH2, and here Cl. Okay. So here, one thing, there will be a, if there is one more molecule, okay, I'll take this compound, straight chain compound, there will be one more molecule, CH3, CH2, CH2, CH2 and Cl. Okay, and here there will be dipole-dipole interaction. One thing, if I write here this compound, if I write here, then here this becomes a delta minus, this becomes delta positive, this carbon becomes delta positive. Here it will again come reacts with CH3, CH2, delta negative, delta positive. Hence dipole interaction will be there. One thing, between these two, dipole-dipole interaction will be there. And also, whenever van der Waals force of attraction, that is London force of attraction also will be there. That is between these non-polar hydrocarbon chain. So, as surface area increases, van der Waals force of attraction also increases. It will get more surface area to interact. So, I'll write like this: as surface area increases, there will be more van der Waals force of attraction. Here in this same isomer of that compound, CH3, CH2, if there is one more compound, it's an isomer, it will become somewhat spherical. So here you can observe more what surface area, but here there will be surface area less. Hence, as branching increases, surface area decreases and boiling point. Surface area decreases means van der Waals force of attraction will be less and boiling point will be decreases. Hence, boiling point decreases with the increase in branching. Hence, straight chain compound shows a greater boiling point. Straight chain compound shows a greater boiling point than a branched. Due to surface area, van der Waals force of attraction will be less in a branched chain compounds. That's about boiling point. And let us see about boiling point of alkyl halides. Now we'll discuss about haloarenes. Boiling point and melting points of haloarenes. See, melting point is mainly dependent upon crystal lattice. How closely packed in a crystal lattice. If you have alkyl halide, any alkyl halide or aryl halide, this alkyl halide, how it is closely packed in crystal lattice, that will depends on a melting point. Suppose if I take alkyl haloarene, dihaloarene, that is dichlorobenzene. First I will take ortho compound. Next one is meta. And third one is para. Right? So ortho position to this, it is meta, is para. Okay. ortho, meta, para. First we'll take